Okay, let's continue. So this is part 3. 6.2. And here I want to start talking about matrices. So basically, here is an idea. When we do linear algebra, there are two ways we can think about stuff we are doing. There is a more concrete one and a more abstract one. For instance, we can think about abstract vector space, but if you want to have a concrete example in mind, which actually helps you to talk about everything, you can take this vector space Fn. And we will later see that every vector space is essentially, every finite dimensional vector space is essentially the same as Fn, isomorphic. And to make this isomorphism, to choose it, you need to choose a basis of your vector space. So matrices will be a concrete basis-dependent form of what we will study next week, which are linear maps, so maps between vector spaces. So today I want to talk about matrices in old school style, basically 19th century style, as some sort of boxes which you can multiply according to some rules and so on. And next week we will answer the question what a matrix actually is, why we define their properties in this or that way, and so on. So today's class, you can think of it as a little bit of a, old 19th century style, very down-to-earth approach to some fun type of algebra of matrices. So mostly I want to talk about it because you see all these notions in practice, they appear in exercises, they appear in other sciences, so it makes sense to just overview a little bit how you talk, what you do with matrices and how that works. Next week you will be able to understand all of that in all detail from much more advanced point of view. So this is a little bit of informal lecture. So what is a matrix? So you can imagine that you have some field in mind. So you have some field, maybe real numbers or complex numbers or something like that. And so a matrix of size n times m is a table where you have, so n by m says that it has n rows, m columns, and then you use double indices to just write down labels here, a11, and the first one is row, and the second is column, a12 up to a1m, a21, a22 up to a2m, and so on, an1 up to anm. So this thing is called a row, and this thing is called a column. So this is a notation, and this is a n times m matrix. And so if n equal to m, then such things are called square matrices. Perfect. So if you look at the collection of all matrices, they usually will be denoted something like m n times m of f. This is a set of all matrices. Perfect. So what can you do with matrices? So the question of why you actually write them in this way is something we will talk about next week. So you can just think of it as, basically f power n plus m, just you write down this collection of vectors not in one long row, but as this kind of table. So there are a few operations with matrices. Some of them are kind of straightforward, some of them are really complicated. So what one can do with matrices? So first thing one can do with matrices is let me call it operations with matrices. So the first one is one can add them, so addition. So suppose you have a matrix. So if I want to write a matrix, some say A, in less like huge way, I will say something like Aij, where I is from 1 to n and j is from 1 to m, something like that. That's a way to write down this kind of matrix. So and then I have B, which is Bij, and necessarily of the same size. So I is also from 1 to n, and j is from 1 to m. Then we can define A plus B is just the same kind of matrix where you sum up Aij plus Bij. And I, again, from 1 to n, and j from 1 to m. So basically, you can sum up matrices, and this means that this thing is an abelian group. So m n cross m is an... So this is a name for the stuff, is an abelian group, whatever it means. I will recall in a second. Group. So what it means that the following axioms are true. So A plus B plus C is A plus B plus C. So all usual properties of addition. Then there is zero such that A plus 0 is A. And this is just, so the 0 is usual notation for this matrix where you have zeros everywhere. And then you know that there exists this minus A matrix where you just take minus signs everywhere. And also there is A plus B equals B plus A. So addition is commutative. That's what's called abelian group. So there is this operation which is called addition. Wonderful. Another operation which is interesting is an operation which is called, you can multiply it on a scalar. So lambda times A, where A is a matrix of size n times m, is also a matrix of size n times m, and this is just lambda times a matrix Aij. So if I don't write here where I and j lie, I mean from n to m, it is just a matrix consisting of this lambda Aij terms. So basically, for instance, if you take 2 times a matrix A11, A12, A21, A22, you just multiply rows and columns by 2. So this is what's happening. And of course, matrices form a vector space. So now we have addition and multiplication on a scalar in F, so lambda is in F. And this vector space m n times m of F over F with basis. Yeah, so with basis, and then the question is, what is the basis? And of course, the basis will be just, because basically this vector space is the same as F n times n, so basically a field n times m times, because you just can think of this vector as, you know, like a long vectors, it doesn't matter. So convenient basis is exactly the one where you have 1 somewhere and zeros everywhere else. So usually you will put 1 in position ij and zeros everywhere else, so just 1 unit, everywhere 0, and this is called usually Eij. So for matrices, you use this basis Eij to talk about them, and this is really convenient. So for instance, let me erase now this part. For instance, if you have 2 by 2 matrices, then these matrices have form A11, A12, A21, A22, and you can write it down in this basis. So this is A11 times the matrix 1, 0, 0, 0, plus A12 times the matrix 0, 0, 0, 1, plus A21 matrix 0, 0, 0, 1 plus A22 matrix 0, 0, 0, 1. And this just says that it is sum Aij, Eij, where I goes from 1 to n and j goes from 1 to m. So this is n and m equal to 2, but in general, this is just true for every matrix. This is the matrix Aij. You can just write it down in this very concise form. So, and then it's clear. So I have just written any matrix in this basis. So remember, this is E1, 1, this is E1, 2, E2, 2, and E2, 1. And so you can also see that every matrix is presented in this way uniquely, because these coefficients are just terms of the matrix. And so it means that m n times m is a vector space of dimension n plus m. N times m. So dimension 4 here, for instance. So this is an example of a finite dimensional vector space, and at the end of this lecture I will show you a cool application of this idea. Okay, so what other things we can do? So if you have a matrix, A, which is this n times m matrix, Aij, this is another way to write it. So Aij is sort of typical term here. This is the usual A11 up to A1m, blah, 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 up to Anm. And then you can define transposition of matrix. A transposed, it's called AT, is a matrix of size m times n. And now I will denote it by Aj. And the definition is just you take your matrix and just flip it. So A transposed Ij, Ij's term of this matrix is Aj. So basically, for instance, if you take a matrix, I don't know, 1, 2, 3, 4, and you transpose it, you get a matrix 1, 2, 3, 4. So you just flip it. The whole matrix, you just flip it. By the way, this material is very standard. If you open Wikipedia page about matrices, then you will easily see all of that. So it's something you can easily find. That's very simple stuff. Okay, so we have transposition, we have addition, and that allows immediately to introduce lots of new definitions, what you can do with matrices, different type of matrices, and so on. So let me do that very briefly. But first I erase everything. Okay, so now let me talk about what I said, addition, transposition. Okay, so there are some types, special types of matrices. So firstly, a remark is that you should be careful, because if you have a matrix of size n times m, then A transposed will have type m times n, just because you flipped the table, and so rows are now columns, columns are rows. So suppose n equals to m. So then there are two special types of matrices. So definition, A is a matrix inside n times n matrix, so n columns and rows, square matrix. A is symmetric if A transposed equals F, and A is anti-symmetric if A transposed equals minus A. So basically, what is symmetric? So let me do 1, 2, 3, 2, 1, 1, 2, 3, 2. This one is symmetric. And symmetric just means that when you look at the main diagonal, it has a symmetry over the diagonal. When you flip, you get the same thing. So you can also say that Aij is symmetric if Aij equals Agi. So you can exchange indices and you get the same thing. And antisymmetric means that, for instance, this one is antisymmetric, 0, 0, 0, 1, 3, 2, minus 1, minus 3, minus 2. This one is antisymmetric. When you flip, all the signs change. And in particular, so this is the same as Aij equals to minus Aji for all pairs of indices. And in particular, Aii equal to 0. So you will always, in the anti-symmetric matrix, you will always have 0, 0, 0, 0. Here you have something, and here you have minus the same stuff. So these two types of matrices will appear in exercises. They are really important. We will study symmetric matrices later on. But for now, you can just think of it as fun examples of stuff you can do with matrices and talk about. So notice both two types of matrices form a vector subspaces of your whole vector space of matrices. And in one of the exercises, you will have to find their dimensions and bases for them. So that are some definitions related to matrices. So finally, there is the main definition, which is the most important thing you can do with matrices, is multiplication. So multiplication. So multiplication is a complicated story, unlike addition and transposition, which are really easy. And so this is what it looks like. So this multiplication thing looks completely weird. Let me first explain, and then I will try to say a few words why it works like that. So you take a matrix n times m. And then you take another matrix of size m times some other number L. And what is important is that your first matrix and the second, the number of columns in the first matrix is the same as the number of rows in the second. And so this one will be called A, this one will be called B. And then you get as a product a matrix of size, which are these two numbers which are different, N and L. So this will be called C. So if, let me say more abstractly, if A is inside n times m matrices, and B is inside m times L matrices, then we construct A times B inside n times L matrices. So I have to say what is the rule, but so far just remember the sizes. So for matrices to be multiplicable, you need the number of columns of the first one equal to the number of rows of the second one. So these two numbers kind of eat each other, and then you have NL matrix at the end. So let's suppose this one is Aij, and this one is Bjk, and then we know that I is from 1 to n, j is from 1 to m, and L is from 1 to, and K is from 1 to L. So then my product, so product is C, so this is C, it's n times L matrix, and I will write it down as C I K. And notice that that's okay because I is going from 1 to n, K is going from 1 to L, and so this has exactly the correct size. So, and then I need to write a formula for CIK. So CIK is basically a term in my matrix C which stands in i's and k's row and column. So what I do, I take the corresponding row here, which has index I. I take the corresponding column here, which has number k. And then I start to multiply elements here on elements here, just this one on this one, this one on this one, and so on up to this one on this one. Notice the number agrees and sum them up. So CIK is sum from j equal 1 to the intermediate index m, A, I, j, B, j, k. So again, I have some index, and then I need to sum along the whole column. I multiply this guy on this guy, this guy on this guy, and sum them up. So aij, bj, k, sum from j equal 1 to m. And that is the rule. So example, let me do a few. So first I can start with something like 1, 0, 1, 0, 1, 0 times, and then this was 2 times 3, and so I need to take 3 times something. So 3 times 2, for instance. 2, 1, 1, 2, 1 minus 1. And so what I get, so first I look at sizes, and so 3 matches here, and they eat each other, and so I have 2 by 2 matrix. And then to get the first term, I take the first row here, the first column here, and kind of multiply them as if I do dot product of vectors. 1 times 2 plus 0 times 1 plus 1 times 1 is 3. Then I do second row here, first column here, 0 times 2, 1 times 1, 0 times 1 is 1. Similarly, 1 times 1, 0 times 2, 1 times minus 1 is 0. 0 times 1, 1 times 2, 0 times minus 1 is 2. And that's the product. Another example is, for instance, I can take the same matrix 1, 0, 1, 0, 1, 0 and multiply it on 1 times 3 matrix, for instance, 3, 1, 0. And what I get is I get 2 by 1 matrix, just because I have 2 rows here and 1 column here, which will be 3 and 1. So multiplying matrices is a little bit of a lengthy process, but it can be nicely done. Perfect. So why on earth do we multiply matrices like that? I mean, there are so many nicer ways. For instance, you can try to multiply, each term on the corresponding term with the same number or something. But firstly, you'll see in a second, I will formulate it. This multiplication has nice properties. Matrices form a ring. N by n matrices form a ring. But later on, you will see that actually, later on, next lecture, we will talk about vector spaces and maps between them. And basically, matrix will be something coding this map in a particular choice of bases. But then if you have a map like that and a map like that, you can take a composition from V1 to V3, and you have compositions of maps. And this product of matrices will be exactly composition of maps. And that's why it has all the beautiful properties it has, and that's why you should define multiplication by this rule. It is a down-to-earth, old-school way to talk about compositions of maps, which we will do next week. So for now, I want to spend a few more minutes talking about properties of multiplication, transposition, addition, and so on. And then I will prove a really fun theorem, which will be a fun application of all this stuff. Okay, so properties, or maybe like theorem. Matrices of size n times n over a field is a ring. So we have operation addition, multiplication, and a ring, I remind you what it means. It means that multiplication and addition have all nice properties except 2. Not commutative, which means AB may not be equal to B. Sometimes it is, but usually it is not. And no division. So there exists a matrix A such that there does not exist B such that AB equal to 1. So you cannot always divide matrices, and order of matrices matters. So these are 2 troubles with the things. Other than that, addition has all the properties which were already listed. Then there are properties of multiplication which hold. Let me go through that actually. So properties of addition we already saw. So there exists a unit matrix 1, which is just 1, 1, 1, 1, 1, 0, 0. And for this matrix, A times 1 is equal to 1 times A is A. More importantly, when you multiply matrices of size n by n, you get a new matrix also of this size. So this operation actually makes sense, because a priori you need to multiply matrices. When you multiply two matrices, you get a third matrix of different sizes than either of those. But when they are square matrices, everything is fine. So this is one property, and identity has all ones on the diagonal, and that's it. Another property is that A times B plus C is AB plus AC. This is really easy. That's called distributivity. And also B plus C times A is BA plus CA. And actually, surprisingly, for matrices, the key property, which is the most important and the hardest one, is just associativity. AB times C is A times BC. There is an easy proof. You can just use the formula I gave you, open brackets there, and you will see that everything holds. But it looks a little bit like a miracle, because, the definition of multiplication was weird, and why it should be true, that's a mystery. So next lecture, I will explain how this is related to linear maps, and so we will prove it. But you can start with, checking it by hand. So, okay, what else shall I say about multiplication? So, some additional things. So, let lambda be inside F. Then you can look at a matrix lambda, 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 zeros everywhere else. And this is the same as lambda times 1, 1, 1, 1, 0. And then we use a notation, which is just a notation, which is denoted by lambda. So these guys are called scalar matrices, and they have this property that at least for these guys, lambda times A is the same as A times lambda, and all terms are just multiplied by lambda. So this is what scalar matrices are. So this is one remark. Another remark is that, what about, so I said sometimes AB is not equal to BA, and you know these examples. And also some matrices don't have an inverse. So for instance, if you have a matrix like 1, 1, 0, 0, then does not have an inverse. Have an inverse. Okay, then one can ask, so suppose you have a matrix. So first, the inverse makes sense only for square matrices. So suppose you have a matrix Aij, which is this one, square matrix A1, 1, up to ANN. And then you can ask, so this is A. When does A have an inverse? So this is a really important problem, because in practice you won't sometimes finding inverse of matrices, just because this is really what solving equations is about and so on. And the answer is that there is something which is called, so this happens, A has an inverse if and only if determinant of A is not equal to 0. So this is some beautiful construction, some element in a field, which for a matrix ABCD is just AD minus BC, but for a huge matrix it will be some very, very long, complicated expression, which we will talk about in lecture class and later classes, and that tells you exactly when matrix is invertible. So this determinant is a long, long, long polynomial in all these letters, and we will talk about it later. What else? Also, very important question. So very important question. Question is how to compute powers, a power n for big N. So this is related to tons of practical applications of linear algebra, and later on we will talk how to do it, and you have seen already some idea in Fibonacci number kind of problem. So this is also important question about matrices, and we will do it later. Next thing which I wanted to say is that suppose, so now I want to talk for a few minutes about polynomials and matrices. So an idea is that you can take a matrix and plug it in a polynomial. So let me erase everything, and then I will explain what does that mean. Okay, before polynomials, let me maybe one more remark. So remark is just quick idea. So this is called matrix form of a system of equations. So let's assume we have a system of equations, which is like a11 x1 plus and so on, plus a1 m xm equal to b1 up to an1 x1 plus an xm equal to bm. Then how one can think about it? So you can write it down in a matrix form. So for that you take a matrix A, which is just this matrix Aij, which is a matrix of size n times m. So this is called a coefficient matrix. And then you can take a matrix which I will call X, which is just a matrix x1 up to xn. And this is a matrix of size n times 1. And because of some reasons which we will talk about later, you can think of these guys as vectors. I mean, we have already seen that this can be thought of a vector in n-dimensional space. So this is sort of the same thing as f power n. But let me ignore it for a second. Oh, sorry, xm. fm, m. And then b is a vector b1 up to bm, which is also a matrix of size, b1 up to bn, also a vector in n times 1, which you can think of fn. And then in this form, your equation is just A times x as a matrix equals to b. And you are trying to find a vector x such that A times x equal to b. And next class we will interpret that as finding a vector x which under a certain map is mapped to a vector b, where x and b are in these two vector spaces. But this is next time. So for now, just an idea is that you can use... Oh, Hermione, come to me. Ups, guys, finally. Ups. Here is one of the cats. Please enjoy. Her name is Hermione. There is also another one, but for now, that's enough. Good. Okay, so ax equal to b. Finally, I want to finish that with a beautiful theorem and a fun idea. So let's suppose that A is an n by n matrix. And let's take a polynomial p, a0 plus a1 t plus and so on plus a m t power m. So notice that if you have a matrix A, you can just plug it inside polynomial. So P of A is just by definition, that's not some theorem, it's just a definition, is A0 plus A1A plus A2A squared up to AM A power M. So why you can do that? Because you know matrices sometimes don't commute, but powers commute. So if you take any such polynomial and multiply it on another polynomial, you can open brackets as usual. So for every polynomials P and Q polynomials, these guys commute. P of A times Q of A. You can multiply in any way you like. So that's a nice observation. Plugging in matrices inside polynomials is really important in all applications, in applications of linear algebra, in computer applications to quantum mechanics, and so on. And basically, to be able to compute such stuff, you also want to know how to compute powers of A, and we will talk about it later. But here is a theorem which I want to prove. So theorem. So for any a matrix, n by n matrix, with coefficients somewhere, there exists a polynomial p which is just a polynomial in one variable, such that when you plug in your matrix inside A, you get 0. So for every matrix, there is a polynomial which vanishes when you plug in this matrix. And let me do an example. So let's suppose that matrix A is just square matrix ABCD. And then you can check that A squared minus a trace of A times A plus determinant of A equals to 0. And trace here, it is just A plus D. So this is just a number, A plus D element in the field. And this is very important. So summing up elements along this diagonal, it's called a trace. And there will be an exercise about that in the next piece. That it's really key thing in linear algebra. Don't ask me why right now, because I won't hear you, and because it takes a little bit of learning the stuff to understand why this is important. But here is a beautiful degree 2 polynomial. So basically, p equal to x squared minus a plus dx plus ad minus bc works. So this polynomial, if you plug in a, you get 0. But theorem tells that for any matrix, there exists such a polynomial. That's an abstract statement, which does not follow from here. So let me prove it. The proof is just one-line proof using a powerful theorem from last class. So I really want you to appreciate it. So consider, let V be a vector space of n by n matrices. So this is a vector space of matrices. So dimension of V is equal to n squared. Remember, when you look at all matrices, they have n. What's going on? Hermione, are you okay? So you have n times m table, and it has n times m terms, and there is a basis consisting of this 1, 0 matrices, and the dimension is the product. In this case, just n times n. So dimension of V is n squared, and so that's cool. So look at vectors. V0, which is equal to 1. So remember, 1 is a matrix. So you can look at this vector. It's some vector 1, 1, 1, 1, 1. If you want, you can even say that this is sort of E11 plus TDD plus ENN, if you wish to. V1 is just A. V2 is A squared. And so on. Vn squared is A power n squared. Yes. So you take all powers up to n squared power, like in 2 by 2 matrices, it will be 0 power, which is 1, first power, second power, and so on, n squared's power. And you can look at these vectors. So notice that, as I said already, multiplication of matrices has nothing to do with vector space structure a priori. And so this will be just some vectors inside this huge vector space. So these are n squared plus 1 vectors. And we have n squared plus 1 vectors in a vector space of dimension n squared. So the number of vectors exceeds the dimension. And remember, every time you have a collection of vectors whose number is bigger than the dimension, they have to be linearly dependent. So there exist numbers a0 up to a n squared in F, such that a0 plus a0 v0 plus a1 v1 plus and so on plus a n squared v n squared equals to 0. So linear combination of these vectors vanishes. But this just implies that 1 times a0 plus a1 times a plus a2 times a squared plus to the a n squared times a power n squared vanishes. But that's exactly the statement that polynomial vanishes. So if you define the polynomial as a0 plus a1t plus and so on plus a n t power n, a n squared t power n squared, then p of a equals to 0. And that proves the theorem. So that's a beautiful application of our theorem about powers of linear dependence for matrices. You found a polynomial which vanishes when you plug in matrix. That's amazing. Notice that degree of a polynomial here equals to 2, though our theorem predicts degree 4 polynomial. So one can ask whether you can do better, and indeed there is a beautiful theorem which is called Hamilton-Kelly theorem, which tells you that there is a specific polynomial called characteristic polynomial, which has degree exactly n, so square root of this guy, and when you plug in a matrix there, you will get 0. So hopefully we will prove this theorem by the end of the course, and this one is a special case for size 2 matrix. In general, it will also have determinant, trace, and some other fun coefficients around. We will do that later. So that's all I wanted to say about matrices, and I will see you next week. So next week, the whole week will be about linear maps. That's very important, and this is the second main idea after vector spaces. See you guys.